Hello, my name's Eric. Today we're going to be doing some calculus. We're going to study some integration techniques. The techniques we're going to cover are found on the harder National High School Calculus exam. I don't think I'm supposed to mention it by name for trademark issues, but you may know that in high schools around the United States, typically two types of calculus are offered. This is the harder one, okay? If you're a college student, you're definitely going to cover these techniques in your college calculus class, first year calculus, okay? So here we have antiderivative we're trying to accomplish for cosine squared. There's a couple of ways to do this. One of these is a good way, one of these is much better. The best way to do this is to remember a trig identity. The trig identity is that cosine squared is 1/2 1 plus cosine 2x. And this is actually the way you would handle an antiderivative for sine squared also, except sine squared has a minus here, otherwise it's the same identity. Okay, we're not going to get into all the pre-calculus about, where does that come from. Just go with it and make a substitution like this. Now you can take the half out of this antiderivative if it makes you more comfortable. And you can actually break this up into two antiderivatives, if that makes you more comfortable. But essentially, you have an antiderivative of 1, which is just x, and then you have the antiderivative of cosine, which is just sine. There is one issue, however. With a 2x here, you're going to have a 2x there, and you're going to have to account for the chain rule. Right? So if we were doing a derivative, the derivative of that interior is 2. We'd multiply by 2. If the interior function is linear, though, and you're doing an antiderivative, in this case, all you would have to do is divide by 2. And so that's where you get an extra little 1/2 out here. Don't forget a constant of integration. And that's how the first problem is solved. So that comes under the topic of special powers of trig functions. We may get to see another one of those soon. Let's go to problem 2. Problem 2 explores a technique called integration by parts. You'll need to know a formula for this, and the formula looks like this. And if you've never seen this before, it's confusing, I'm sure. But the idea is you're going to break this apart in such a way that something here is going to be represented with a u, and everything else is going to be called dv. Probably the best way to do this is to pick this to be the u and this to be the dv. Now why is that? Well, I can give you a couple reasons. One, there's a little acronym I ran across a few years ago, and it helps you prioritize your choices. Choices for u and choices for dv. So it turns out that functions near this end of the acronym, I don't know how you say that, laity or whatever, these would be good choices for dv. Whereas if you're up near this end, these are good choices for u. So that can help you pick. But another way to do it is say, if u is x, at some point you're going to have to compute du, which means you'll have to do the derivative. And the derivative of x is 1, and that makes things more simple. I mean, what's complicated about this in the first place? There's a variable here and a variable here and a multiplication in between. And that is why we are having to appeal to this formula in the first place. So, you come over here and you say, I've decided to let u be x. I'm going to, at some point, need the differential du. And we know that that's u prime times dx. Okay, well, u prime is just 1. And so it turns out du and dx are equivalent things in this problem. Everything else here is dv. Now, in this formula, you're going to need to know what v itself is. So that gives you sort of an antiderivative problem you have to solve right now. Maybe put a 1 in front of this. And take the antiderivative on both sides. And over here you'll get a v, and on the right you'll get sine. Now I typically don't go through all those steps, and I'm going to save my constant of integration until later. But v equals sine. Now from here down, all you have to do is pick pieces out of that array to compute what you see here. So what's u? X. What's v? Sine. So you're multiplying down this way. So you have x times sine, and then minus the antiderivative of v times du. Well, here's v, and here's du. So I guess for v I put sine, and for du I put dx. Okay? We still have an antiderivative we have to do, but it's not like this one where it had variable times variable. Now I just have a trig function. What is an antiderivative for sine? Let's see. Cosine's derivative is negative sine. So it must be negative cosine. And yes, I have minus here. I should clean that up because it's ugly. So here's the best answer in my opinion. X times sine x plus cosine x plus c. And believe it or not, if you took the derivative of this, you get some cancellations and things, and it would come back to that. It's the truth. Okay? So that's how that problem is done. And we move on to a new problem, actually with a new technique. This problem involves something called partial fraction decomposition. So the idea is, it comes from algebra. Before you go and try to do an antiderivative, we don't really have a good formula for doing antiderivatives of quotients of things. So when you have one polynomial divided by another, when you have a rational expression, not always, but a lot of the times, this technique called partial fraction decomposition can help. So forget the antiderivative for just a minute. Let's just study this. Now what you want to do is replace the denominator with its factored form. And that's going to be x plus 4, x minus 3. Then you'll set this equal to two fractions, each of which sits each of which has one of these binomials in its denominator. Now what's a and what's b? Well, that's what we have to find out. So but it turns out there are two fractions that look like this that can add up to make that if you just pick the right a and b. The technique for picking the a and b, there's a really good shortcut for this. Maybe I'll show you right near the end of this problem. But for now, I'll do it the traditional way. Next, what you do is you multiply x plus 4, x minus 3 on both sides of this. So what does that look like? that looks like this. But if you're going to do it to the left, you have to do it to the right. I know, it's getting pretty ugly. Well, it's going to get better. Hang on, hang on. X plus 4 is going to cancel. X minus 3 is going to cancel. You're going to be left with 8x plus 11 on the left. And then on the right, you get some cancellations also. When these two factors multiply against this fraction, the x plus 4 is canceled, but the x minus 3 is not. So you're left with a times x minus 3. Similarly, when this fraction multiplies these two factors, the x minus 3 is canceled, but the x plus 4 does not. So you're left with b times x plus 4. Now, I think it gets kind of fun from this point out. This equation is supposed to hold true regardless of what x is, so you can pick any x you want that you think may help you figure out what a and b are. For example, you can pick x equals 3. And watch what happens. You get 8 times 3 plus 11. And then over here, you get a times 3 minus 3 plus b times 3 plus 4. Well, that's 24 plus 11 is 35. And that's pretty clearly 0 right there. And over here, you get 7b. So what does b equal to? B is equal to 5. Now I'm going to do a little erasing here, and I'm going to pick a different number other than 3 to plug in that will help me. Can you figure out what it is? Yeah, it's x equals negative 4. So pick x equals negative 4 and just plug it in. So you have 8 times negative 4 plus 11. On this side, you have a times negative 4 minus 3. And I might as well not even write the last one down because, I mean, why did I pick negative 4? Negative 4 plus 4 is 0. I'm trying to kill off that b so I can focus on the a. But just to be thorough, I'll put it in there and make some final comments. Okay. Negative 32 and positive 11 makes negative 21. Negative 4 minus 3 makes negative 7. And as I already mentioned, there's nothing over here except 0 times b. Divide by negative 7, and you'll learn that 3 equals a. We haven't even done any calculus yet, but here's the thing. We can now do this problem in a different way. We can do it like this. An antiderivative of these two things. Now that we know what a is, and now that we know what b is. Furthermore, you can break this up into two different antiderivative problems. One that looks like this, and factor the 3 out of the antiderivative, and then you can do this over here also. Okay, hope that's clear. Now these, of course, are just natural logs. Like if I had 1 over x, you know that's natural log. It's not really any different with x plus 4. Sometimes you have to be a little bit careful with chain rule and things like that, but no, we're good. Now, if my student gets this far, I'm just thrilled. They did it right. Nice job, and so forth. But there are log properties that allow you to make this, I don't know, a little more compact. Some people would say it's more efficient. What are those log properties? Well, for one, you can, since these are both multiplied logs, you could treat these multiples as exponents within the log. that would look like this. And this. And then, because a log plus a log is a log of a product, we can write this as a single log of the absolute value of x plus 4 to the third power, x minus 3 to the fifth power, close the absolute value, write plus c, and you are done. Okay, I'm going to break this video off right here, and I'll do a little bit more of this in the next video. Have a good day.